The next question of CodeForces round 923 DIV3 is microcycle. So basically in this question, we are given a graph with n nodes and m edges. So the given graph is a undirected graph. It's a undirected weighted graph. So basically in this graph, for each edge, we are given some weight. So let's say the graph is as follows. So and one more thing that is guaranteed here is uh, in this graph, there won't be any self loops. Self loops are loops which are in this fashion, or like basically a edge to the node itself. And it is even guaranteed that for every edge, there is at most one for every between every pair of nodes, there is at most one edge. That is from 3 to 7, there is one edge. Now there can't be one more edge from 3 to 7. So there is at most one edge. Such a way a graph is given. Now in this graph, we need to find out a simple cycle. So what, according to the question, a simple cycle is a closed loop which has every edge exactly once in it. So 1, 5, 8, 7, 4, 2 is a simple cycle. Similarly, 2, 3, 10 to 2. This is a simple cycle. So this kind of things are called simple cycles. Now, if we consider only 1 and 5, so you might think 1 to 5 and 5 to 1 might also is also a cycle. But this is a cycle, but it's not a simple cycle. Because if you see, edge between 1 and 5 is included twice. And similarly, one more example is 2 to 3, 3 to 10, 10 to 2. And again, repeating this cycle twice is also not a simple cycle. As here, there is at least one edge which is appearing twice. So, so basically, simple cycle is a cycle in which each edge is considered only once. Now, for each edge, we are given some weights, W1, W2. Okay. Now, among all these simple cycles, we should print any one simple cycle uh, in which there is an edge with the lightest weight. That is basically here, let's say we have two simple cycles. Here we have two simple cycles. So among these two simple cycles, we should print the cycle. So we should print the cycle in which the edge is minimum. Basically, for this simple cycle, let's say the weight of uh, the weight of the minimum most edge. Basically, if we consider an edge in this, which is the minimum most. So let's say W1 is the edge which has the smallest weight among all the edges present in this cycle. And let's say from this cycle, W8 is the smallest edge among all the edges present in this cycle. We need to output the cycle which has smallest weight, smallest such weight. That is in the cycle, the smallest weight edge should be as minimum as possible. So there can exist multiple cycles also, multiple simple cycles which has the smallest weighted edge also. So in that case, we can print any of the cycle. And while printing the cycle, the order doesn't matter. We can print this, let's say for this, W1 is the minimum most weighted edge among all the edges, and from this cycle, W8 is the minimum most weighted edge. And among these two weights, W1 is the smallest. Then our output should be this cycle, right? So we can print this cycle as 1, 2, 1, 5, 8, 7, 4, 2. Or we could even print it as 8, 5, 1, 2, 4, 7. So we can print this cycle in any order. Order doesn't matter. So now for the given graph with n nodes and m edges and with certain weights for each edge, we should output what is the minimum weight of the simple cycle possible space the length like space the number of nodes in the simple cycle, and we need to output the simple cycle nodes in the simple cycle. Basically, we need to output the nodes in the simple cycle starting from some start node and in the order of the cycle. So this is how the output should look like. And if we look at the constraints, here there can be test cases in the range 1 to 10 power 4, and it is given that number of nodes is at least 3 and m is greater than n. So we can observe that this guarantees that because m is greater than n, and it is also guaranteed that between two pairs there won't be multiple edges. So from these constraints, we can observe that for sure in the given graph there will exist at least one simple cycle. So, and it's even guaranteed in the question. So from the constraints also we can observe that there'll at least exist one simple cycle. And m is still minimum of n into n minus 1 by 2 into 10 power. And here if we see the edges given u and v can be in the range 1 to n, and weight of each edge can be in the range 1 to 10 power 6. And it is guaranteed that summation of m over all test cases won't exceed 2 into 10 power 6. So this is the question. Let's see how we can solve this. So to solve this question, the prerequisites are you should know disjoint set union, and you should know DFS, depth first search, and you should have knowledge on graphs. Now let's see how we can solve this. So basically, let us divide it into two parts. Our first aim is to find out the any one edge which belongs to a simple cycle, and the weight of that is as minimum as possible. smallest, right? So basically, firstly we are finding out. Firstly, our aim is to find out the edge which will belong to some simple cycle, and the weight of that edge is as smallest as possible. Because for our first aim is to find our because our aim is to find out a cycle with the smallest weighted edge, right? Find out a simple cycle with the smallest weighted edge in it. So, if for suppose we got some edge u to v, which belongs to a simple cycle and the edge weight is the smallest, then our answer will be the smallest weight, because this will obviously be the smallest. This will obviously be the smallest weight for some cycle, but we don't know which cycle it is. So now we know this is the weight that is the smallest, but now the task is to retrieve the cycle. So firstly, let's find this out, and then let's see, using this v and u nodes, how do we retrieve the cycle, simple cycle, right? So here, to find this weight, we'll be doing disjoint set tuning, DSU. So now the way we can do DSU is, we can just sort all the edges. Why? Because we can observe that it's always beneficial for us to connect all the edges with higher weight, because uh, because more the higher weight edges we include, better will be the chance for the graph to be connected. So here we are not connecting the graph, but from a disjoint state of the graph, we are connecting to detect a simple cycle with the smallest edge weight. So, initially we can assume that all the nodes are just separate, completely separated, so on till n. Right? All these nodes are completely separate. Now we have some set of edges, right? So let's say the edges are of the form u to v. This tells there is an edge between u to v with a weight w. Now let's sort edges with weights in decreasing order. Right? So we are sorting the edges with weight in decreasing order. Now, once we sort these edges with weight in decreasing order, we can just keep applying DSU, right? We can just uh, iterate over all the edges in this order: U, V, and W. Now this edges is modified, this edges is sorted based on this condition. Now, let's say DSU, uh, let's consider that DSU has two functions: union of U comma V. So people who don't know disjoint set union, you can go watch, you can go learn disjoint set union and then watch the video from this point. So now, uh, let's say D is some structure and D dot union of U comma V will merge. Let's assume that D dot union of U comma V will merge subtree of U. Basically, will merge the graph of U and V, right? If they are not connected, and D dot find of U, let's say it gives us the leader of graph U. Basically, uh, if we do D dot find of X, then let's assume that it gives leader of graph X. right? So now we are using disjoint set union to detect whether there is a cycle or not. And we and because we want a simple cycle with edge having minimum weight, we are just detecting when we add a edge with minimum weight, then whether a cycle formed or not. Right? So that's what we are detecting. So here our aim is at the instinct we added a edge, did a cycle form or not? We added a edge u comma v with weight w, then whether a cycle formed or not. Right? So in case if cycle forms, then for the so formed cycle, we can guarantee that for sure W will be the smallest edge weight. Why? Because we are merging the, if we observe this, the reason why we sorted is we are merging the edges based on the largest weight. So when we are connecting u comma v, basically uh, when we are when we merged u comma v, then let's say a cycle formed, we could detect that a cycle got formed. Then we can guarantee that for that cycle which is formed, the minimum weight edge will be from u to v, and the weight of that is w. Right? Why? Because we know that because we are following the order of decreasing order of weights till the point where we connected u to v, we connected all the edges with weights greater than u to v only, greater than or equal to u to v only. But due to connecting the current edge, a cycle formed. That means for sure the current edge should only have the minimum weight, right, in that cycle, because all other edges have weights greater than or equal to w. As we are moving in a descending, we are traveling in a descending order of edge weights and merging them. Right? So if we look at this thing, if you look at it in this fashion, then we can just iterate over edges. And now the way we can detect the cycle is if d dot, basically if d dot find, in case basically if u and v are already connected and now we are trying to connect u and v again, then we can say a cycle is formed. Okay? So basically if u and v are connected, then the leaders of u and v will be same. So if both u and v have the same leaders, kind of, if these two have the same leaders, then the minimum weight, let's call it as answer. So the smallest weighted simple cycle could have a weight w, because after connecting u and v, because yeah, because after connecting u and v, now a simple cycle forms. Okay? And our starting node could be u and our ending node could be v, right? Or we can take it reverse also. Starting could be v and ending could be u, because we know for sure uv will be included in some simple cycle. So because while printing the order doesn't matter, else that means they are not connected, so we need to merge them. U comma. So now we need to connect them. Okay? And we know these are sorted. This is sorted in descending order of weights. So because it's sorted in descending order of weights, as soon as we encounter that any node belongs to a simple cycle, we can just set its values, and we can guarantee that always this W will be the minimum most weighted edge. This W will be the minimum most weight of the edge present in the simple cycle that is formed. And among all the simple cycles that are present, W will be the smallest edge of some simple cycle. So, and that simple cycle will include nodes U and V. Okay? So now from this, we could like we by doing this, we could retrieve a edge between S to E with a weight answer, right? We could retrieve that. And we know that this is the edge which has the smallest weight and belongs to a simple cycle. So now we know the answer, like now we know the smallest weight possible for a simple cycle, which is answer. Right? And we could retrieve the edge also. The edge which is contributing to some simple cycle, which gives the minimum answer. So that was our first case, right? Now, because we detected it, 60%, 50% of the task is done. We know what is the answer, and we know which edge is actually contributing to give this as our answer, right? Basically, this which edge is contributing to a simple cycle with the smallest weight. Now, if we see, we know that in the simple cycle with answer as the weight, S and E are some nodes, right? Now our aim is to find out from S, starting from S, all the nodes which will travel and come back to S, right? Or let's say let's basically find out this, that is basically S is the starting node and E is the ending, let's say. We need to find out all the nodes in the simple cycle, which looks like this, right? So we need to find out what is this node, what is this node, what is this node, what is this node, what is this, what is this, what is this, right? So now to retrieve this simple path, and there can be multiple such paths also. Let's say, let's say there are two such things. Though there are two such things, we can just retrieve any one, right? So we can just perform a DFS and retrieve any one of them. As soon as we get any one path, we can just retrieve. So now let's say for now, this is the path and we need to retrieve this, retrieve the node values of this, all these. So for that, what we can do is, we know for sure E will be present and S will be present. Basically, S and E are present in the simple path, simple cycle, are present in the simple cycle. And we are assuming that S is the starting point of the simple cycle. So we'll be constructing the simple path, assuming S is the starting point of the simple cycle and E is the ending point of the simple cycle. Now, if we look over, what we can do is, we know that from it is guaranteed in the question that for every pair of nodes, there will exist only one edge, at most one edge, right? Every pair of nodes U to V, there will exist at most one edge. We know this. because we know this now, what we can do is, let's say we have some graph, some random graph here, something like this. This is some random graph, and we know we need to find a simple cycle which includes S and E as the edge. Then what we can do is, we can just remove this. Let's say we built adjacency list for this graph. To find out any one simple path, we can just remove this edge between S and E. And now what we can do is, from S, we can find out any one we can find out any one path which starts from S and ends at E, right? So if we find out that path, then the answer, then we could retrieve the cycle. We could retrieve the simple cycle, right? So for that, start doing a DFS considering S as the source, and maintain a global variable, maintain some variable. I mean, maintain some list to track which path it is, and ensure that you don't create, for every DFS call, you don't recreate the path. Instead, keep updating on the same memory location of that path. So, and then implement it, and then implement it in such a way that you could retrieve a path which starts from S and then ends at E. So you can retrieve any path. In this case, there exist two paths. So from S, either this could be the answer or this could be the answer, because both of the simple cycles include S and E as the edge. So no matter which one you retrieve by doing a DFS, it's fine. So now here, what we can do is perform a DFS. Firstly, remove edge. Edge between S to E. Remove this from adjacency list. Assuming that we are maintaining adjacency list of the graph. Now remove this. Once we remove this edge from the adjacency list, it just breaks down to a graph which don't have this edge at all. Right? So now on that graph which don't have this edge at all, we can perform a DFS starting from S and then find a path ending at E. Right? So perform a DFS from S and find a path ending at E. Then we can say that our answer is nothing but the path that we got, right? So the path will look like S comma some x1, let's say node. So S node 1, node 2, so on till n, right? So this will be the path. So finally our answer will be answer comma length of path and then output the path. Output the path retrieve. So for this path, we fixed starting to the S and ending to the, and then we are finding out the path. So here one more thing, why we are removing edge between S and E is, if we have edge between S and E, we might retrieve a path which is from S to E only, right? But if we see S to E is a cycle, but it's not a simple cycle. From S, we can go to E and come back from E to S. That is basically, we can use the same edge, go over here and come back. But here, this violates the given conditions of simple cycle. That is, if we see this edge is included twice in the path, so we can say this is not a simple cycle. To ignore, when we are doing DFS, to ignore getting a path from S to E directly, we are removing this direct edge and then finding out a path from S to E in the graph which don't have an edge between S and E. Then we can say that that is a path, right? And we know that for sure in that path there will exist at least one more node. At least one node will exist, like between after removing S and E's edge, between S to E's path, there will be at least one node. Yeah, there will be at least one node. That is because it is guaranteed that between any two pairs, it is guaranteed that between any two pairs, there can at most exist one edge, not more than that. So from these observations, we can see that we'll always retrieve a valid simple cycle by just removing a edge from S to E from the graph and then performing a DFS considering S as the start node and E as the end node. Okay. So as a quick gist, firstly we do DSU, sorting the edges in descending order of their weights to find one edge which has the smallest weight and which belongs to a simple cycle, right? And the edge is SE and the weight of that is answer. So answer will be the required answer as that is the smallest weighted edge which belongs to some simple cycle. Now our task is to retrieve the simple cycle which contains S and E edge. So for that, we are considering S as the start point and E as the ending point, and then removing the edge between S and E to ignore the path, uh, to ignore the direct path from S to E, and then we are performing the DFS on the modified graph where we remove edge between S and E. So while performing DFS, we are starting from S and then finding out any path which will end at E, right? So once we get that path, the answer, we can just print the answer and the required path. Right? So this way we can solve the problem. So let's see what is the time complexity of this. So the time complexity of this would be so here we are basically doing a disjoint set union, right? So firstly, to sort the edges based on the weight in descending order, it will cost us n log n. Okay, let's say m log n because number of edges are m here. This is to sort. Plus, we are performing disjoint set union on the nodes. So let's assume disjoint set union per union call. Let's assume it takes log n, but it's not perfectly log n. Most of the times it's very lesser than log n. It is almost big of 1. But as it has a worst case, let's assume it's log n. Assuming per call in the worst case, disjoint set union takes log n. The time complexity is n log n to perform disjoint set union. Plus now after we retrieve start S and E, the edge between S and E, basically after we retrieve the edge S and E, we are performing a DFS. So assuming that DFS takes number of nodes plus number of edges in the worst case, the time complexity will be m log m plus n log n plus n plus m, right? In the worst case. So we can just round it down and say it is big O of m log m plus n log m. Yeah, m log m plus n log m. Considering the big terms. And if we look at the space complexity, here space complexity depends on how you implement. So assuming we use a array, I mean, assuming we use a global array to find the path and we maintain one visited array also, we can say space complexity would be, and in disjoint set union, we need a big of n space, right? So assuming all these, we can say space complexity will be n on an average. So if we consider practically, we can say for disjoint set union, we need an array of size n, and we maintain a visited array of size n, and we maintain a path whose length can at max be n, right? So it would be 3 into n, and we can just round it down and say space complexity is n. N in the worst, we can just round it down and say space is n. So all this is per test case. It's big of n. This is rounding it down, so it's big of. So time complexity is big of m log n plus n log n, and space is big of n. Rounding everything down to big O. Now, like all this is per test case. So this time complexity and this space complexity is per test case. And here we see n and m depends on the test cases. So if we look over, it is guaranteed that summation of m is always less than or equal to 2 into 10%. And we even know one more thing, that n is always less than or equal to 2. So in the worst case, we can assume there is one test case with n perfectly 2 into 10% and m perfectly 2 into 10%. Right? So considering this as the worst case, still the time complexity and space complexity is sufficient enough to pass in a TL of 4 seconds. So here 4 seconds of TL is given. So this time complexity is sufficient enough to pass in a TL of 4 seconds. And memory allowed is 256 MB. And big of n memory is sufficient enough to fit in 256 MB of memory limit. So this way we can solve the problem.